Roughly 700 people have left the atmosphere. That is a small enough number to fit in a lecture hall, and it means the entire human sensory record of space, everything anyone has directly seen, heard, or smelled out there, comes from a sample group smaller than a rural high school. That sample has produced a strange archive. Scattered through flight transcripts, debriefs, and post-mission medical interviews are observations that nobody planned for and nobody quite knew how to file. Lights appearing behind closed eyelids in a darkened module. An odor in an airlock where nothing had burned. Particles drifting past a capsule window at sunrise, moving with the spacecraft rather than past it. Tapping against a pressure hull with nothing outside to do the tapping. These reports have a specific evidentiary quality worth noting. The people making them were selected, in part, for their resistance to embellishment. Test pilots, physicians, geologists, engineers. Professionals whose careers depend on the difference between what occurred and what it resembled. When one of them reaches for a comparison, it is usually because the vocabulary genuinely ran out. Buzz Aldrin describing lunar dust as smelling like spent gunpowder was not being colorful. He was a man with a doctorate in astronautics reporting a smell. Most of these observations now have explanations, and the explanations tend to be the better story. The lights are heavy nuclei from dead stars passing through living retinal tissue. The airlock odor is a chemical signature of atomic oxygen recombining on cold metal. The particles were frost, shaken off the spacecraft's own skin. A few remain unresolved, and a few resolved into something more consequential than a curiosity, including a region above the South Atlantic where the planet's magnetic shield thins, computers fail, and the physics is still in motion. Astronauts began reporting it during Apollo, and the reports were consistent enough to be taken seriously immediately. In darkness, the module lights down, eyes closed, drifting towards sleep. A flash would appear. Not a general brightening, but something with structure. A streak, a point. Occasionally a starburst, and occasionally something the crews described as a double flash separated by a fraction of a second. Buzz Aldrin mentioned it during an Apollo 11 debrief almost in passing. Others on later missions found the flashes frequent enough to interfere with sleep, occurring perhaps once or twice a minute during quiet periods, always when the eyes were dark adapted, and usually when the eyes were closed. The last detail is the one that mattered. Light entering through the pupil requires the eye to be open, or at least requires the eyelid to be thin enough to pass it, and eyelids pass only a diffuse red glow. Nothing with edges. Whatever was producing these events was not arriving as light. It was arriving as something else and being converted into a visual sensation somewhere inside the head. The physicists had a candidate before the astronauts ever left the ground. Cornelius Tobias had proposed in the early 1950s that a sufficiently energetic charged particle passing through the eye might produce a visual response, and he had gone as far as to put his own head in front of a particle beam at Berkeley to check. He saw something. The idea sat mostly dormant until crews in cislunar space, outside the protection of the magnetosphere, started describing precisely what the model predicted. The mechanism turns on what a cosmic ray actually is. The term is misleading. These are not rays in the sense of light. They are bare atomic nuclei stripped of their electrons, accelerated to a substantial fraction of the speed of light by processes we still do not fully understand. Most are protons, single hydrogen nuclei, a smaller fraction are helium, and a smaller fraction still are what the radiation community calls HZE particles, high atomic number, high energy, iron nuclei, carbon, oxygen. Each one carrying the mass of an entire atomic core and moving fast enough to cross the diameter of the Earth in a fraction of a second. When one of these passes through the human eye, several things can happen, and the crew's descriptions map onto them with a precision that took decades to sort out. The simplest is direct ionization. The particle plows through the retina, and along its path it strips electrons from the molecules it encounters. The retina's photoreceptors are chemical detectors. They exist to register energy deposition and report it to the optic nerve. They do not care where the energy came from. A photon of the right wavelength triggers a response. So does an iron nucleus tearing a channel of ionized molecules through the same tissue. The nerve fires. The brain receives a signal on the visual channel and does the only thing it knows how to do with a signal on the visual channel, which is to render it as light. The streak the astronaut perceives is, in a real sense, a map of the particle's trajectory across the retinal surface. The second mechanism is Cherenkov radiation, and it accounts for the flashes that crews described as diffuse rather than linear. Light in vacuum has a fixed speed limit. Light in a medium does not travel at that limit. In the vitreous humor filling the eye, it moves at roughly 3/4 of its vacuum speed. A charged particle entering that fluid at 99% of vacuum light speed is therefore moving faster than light moves in that particular substance. Nothing about relativity forbids this. What happens is analogous to a supersonic aircraft. The particle outruns the electromagnetic disturbance it generates, and the disturbance piles into a conical shock front. The result is a faint cone of blue light, generated inside the eyeball itself, sweeping across the retina. Reactor cores glow blue for exactly this reason. A person experiencing a Cherenkov flash is briefly a very small, very dim reactor. Distinguishing the two took real work. The instrument used was, for a period, the astronauts themselves. During Apollo 16 and 17, crew members participated in a formal experiment. A blindfolded observer would report each flash, its apparent position, and its shape, while a passive detector, a stack of plastic sheets that records particle tracks as microscopic damage trails, was strapped to the head. Afterward, the plastic was etched and read, and the recorded tracks were compared against the timed verbal reports. The correlation held. The particles were arriving, and the eyes were reporting them. Later, work aboard Mir and then the International Space Station refined the picture with better hardware. The Psyli experiments used silicon detectors mounted in front of the eyes, allowing researchers to characterize the specific particle, its charge, its energy, its path, associated with an individual reported flash. The results confirmed the two-mechanism model and added a third possibility: nuclear interaction, in which the incoming particle strikes a nucleus within the eye tissue directly, shattering it and sending a spray of secondary fragments through the surrounding cells. This produces the starburst descriptions, and it is by some distance the most destructive of the three. That word, destructive, is where this stops being a curiosity about perception and becomes a problem in mission design. Each flash is a particle passing through neural tissue. The retina and the optic nerve are central nervous system tissue, extensions of the brain that happen to sit at the front of the skull. And central nervous system tissue does not regenerate the way skin or bone marrow does. A photoreceptor killed by an iron nucleus is not replaced. The dose from any single particle is negligible in the conventional sense. Radiation exposure is normally measured as energy deposited per unit mass, averaged over a tissue volume. And by that metric, an individual HZE particle contributes almost nothing to an astronaut's total. But averaging is exactly the wrong operation here. The energy is not distributed. It is deposited in a column a few nanometers wide, running through whatever happens to lie along the particle's path. Along that column, the local dose is enormous. Cells directly on the track can be killed outright. Cells adjacent to it receive a shower of secondary electrons. The radiation community calls them delta rays. That damage DNA in patterns unlike anything produced by X-rays or gamma exposure on Earth. Terrestrial radiation biology is built almost entirely on sparse, low-density ionization. Heavy ions produce dense, correlated damage. Multiple double-strand breaks clustered within a few turns of the DNA helix, which the cell's repair machinery handles poorly because it evolved assuming damage would arrive one break at a time. There is an analogy that captures the geometry, if not the scale. Imagine a rifle bullet fired through a stack of paper. Measure the total mass of paper removed and it is trivial, a few milligrams. But the hole runs through every sheet and no sheet is intact. Now consider that the stack is a piece of the retina, and the sheets are individual cells arranged in the precise architecture that makes vision possible, and that the paper cannot be replaced. Crews near Earth are partially shielded. The magnetosphere deflects a large fraction of incoming charged particles, and the ISS orbits well inside it. Even so, station crews report flashes, most frequently while passing through the South Atlantic anomaly, a region where the inner radiation belt dips unusually close to the surface. Apollo crews traveling beyond the magnetosphere entirely had no such protection. They were exposed to the raw galactic cosmic ray flux, which is why their reports were so much more frequent, and why the phenomenon was discovered on lunar missions rather than in Earth orbit. This creates an uncomfortable asymmetry for anyone planning a Mars transit. The magnetosphere ends. The flux does not decrease with distance from Earth. Galactic cosmic rays arrive from all directions, isotropically sourced from supernova remnants and other accelerators scattered across the galaxy. Some of the iron nuclei striking a spacecraft in interplanetary space were accelerated by a stellar explosion that occurred before the solar system condensed. They have been traveling ever since, spiraling along the galaxy's magnetic field, and their journey ends inside a human eye somewhere between Earth and Mars. Shielding does not solve this cleanly. Aluminum is adequate against solar protons but performs poorly against heavy ions, because stopping a heavy nucleus means fragmenting it, and fragmentation produces a cascade of secondary particles that can be more biologically damaging than the original. Adding aluminum can, in some energy regimes, make the radiation environment inside worse. The materials that perform best are hydrogen-rich, polyethylene, water, even the crew's own food and waste, because hydrogen nuclei are efficient at absorbing energy without generating heavy fragments. But the required mass is substantial, and mass is the currency in which spaceflight is denominated. So the question that emerges is not really about the flashes. Those are incidental, a side effect that happens to be visible because the retina is the one piece of exposed neural tissue with a reporting channel. The real question is what the same particles are doing to the parts of the brain that cannot report. Rodent studies at heavy ion accelerators have found measurable deficits in attention, memory, and behavioral flexibility after exposure comparable to a Mars round trip, along with structural changes in dendritic architecture. Whether those results transfer to humans is unresolved, and the sample size for testing it directly is 0, which leaves the flashes as something closer to a warning light than a curiosity. Everyone is a confirmed hit on nervous tissue. On a long transit, a crew member might see several thousand. The ones they see are the ones that happened across the retina, a target of a few square centimeters. The brain behind it presents a target several hundred times larger, and it is silent. And the eye is not the only sense that reports things it was never designed to detect. There is also the matter of what a spacewalk smells like, and why the odor appears only after the airlock repressurizes. The reports are consistent enough that they have become part of the informal vocabulary of the astronaut corps. A crew member comes in from an extravehicular activity. The airlock repressurizes. The helmet comes off, the suit is removed, and there's a smell in the compartment that was not there before. It clings to the suit fabric, to the gloves, to the tools brought back in, to the hatch mechanism. It fades over a few hours, and every attempt to describe it lands in roughly the same territory. Don Petit, an ISS crew member with a doctorate in chemical engineering, which makes him an unusually well-qualified nose, described it as a distinctly pleasant metallic sensation and reached for the comparison of a welder's fumes after arc welding, the sweet, acrid smell that hangs around a shop floor. Others have said seared steak, ozone, hot brake pads, gunpowder, though that comparison belongs more properly to lunar dust and gets conflated. Thomas Jones described it as sulfurous. Tony Antonelli said space smells strange, and then declined to improve on that. The common thread across a couple dozen independent accounts is metal and burning, from people who know perfectly well that nothing in a vacuum can burn. That last point is worth sitting with, because it is the constraint that makes the phenomenon interesting rather than trivial. Combustion requires an oxidizer in sufficient density to sustain a reaction. The environment outside the station has a particle density on the order of 100 billion particles per cubic centimeter, which sounds like a great deal until you compare it to sea level air at roughly 25 quintillion. It is a vacuum by any laboratory standard, better than most vacuum chambers on Earth achieve. Nothing burns there. There is also no medium to carry an odor. Smell requires molecules to travel from a source to a nasal receptor, and in a hard vacuum there's no bulk transport, no diffusion in the ordinary sense, no air to carry anything anywhere. So the smell cannot be the smell of space, strictly. Space has no smell, in the same way that it has no sound. What the crews are perceiving is something that space did to the objects they brought back with them, released into the compartment once there was air again to carry it. The leading explanation centers on atomic oxygen, and it requires a short detour into what low Earth orbit is actually made of. At the station's altitude, somewhere between roughly 400 and 420 kilometers, depending on the reboost schedule. The residual atmosphere is not the mixture we breathe. Ultraviolet radiation from the sun, at wavelengths below about 240 nanometers, carries enough energy to break the bond, holding an oxygen molecule together. At sea level, this rarely matters, because the atmosphere above absorbs those wavelengths before they arrive, and because any freed atom immediately collides with something and recombines. In the thermosphere, neither condition holds. The ultraviolet arrives unattenuated, and the density is low enough that a freed oxygen atom may travel a considerable distance before encountering a partner. The result is that the dominant species in the region where the station flies is not molecular oxygen or nitrogen. It is monatomic oxygen, single unpaired oxygen atoms, which are among the more aggressive chemical species available anywhere in nature. An oxygen atom wants an 8th electron. It wants one badly enough that it will take one from almost anything it touches. This is not a theoretical concern for spacecraft designers. Atomic oxygen erodes materials in orbit at measurable rates. Early shuttle missions found captain insulation visibly degraded after a few days of exposure, and the effect is now routinely accounted for in materials selection. The station's exterior is continuously being sandblasted by a flux of atoms, each looking for an electron. Now consider a spacesuit moving through that flux at 8 kilometers per second. The suit's outer layers, its tools, its tethers, its handrails all accumulate atomic oxygen. Adsorbed onto the surface, adhering to the cold metal and fabric, unable to react further because in vacuum, there is nothing else nearby to react with. The suit comes back into the airlock carrying a monolayer of one of the most reactive species in chemistry, held in suspension by the simple fact that it has had no opportunity to do anything. Then the airlock repressurizes, and the opportunity arrives all at once. The adsorbed atoms find partners. They pair with each other to form molecular oxygen. Some form ozone, triatomic oxygen, which has its own characteristic sharp odor familiar to anyone who has stood near an electrical arc or a photocopier. Others react with whatever organic compounds are present on the suit's surface, and with hydrocarbons in the cabin air, producing a range of oxidized fragments in trace quantities. Each recombination releases energy. The net effect is a burst of low-level chemistry across every surface that was outside, concentrated in the moments after pressure returns. This is the mechanism, but there is an aspect of it that explains the specific character of the descriptions. The compounds most often implicated are short-chain oxidized hydrocarbons and notably polycyclic aromatic hydrocarbons, the same family of molecules produced when organic material is heated to the point of partial decomposition. They are what you smell in a barbecue, in a coal fire, in a burnt engine. The human olfactory system is very good at detecting them at low concentration, presumably because for most of our evolutionary history, the presence of these molecules meant fire, and fire mattered. So the perception makes sense. The crew is not smelling combustion. They are smelling the products of combustion chemistry occurring without combustion. Oxidation reactions reaching their endpoints without the heat, the flame, or the sustained reaction front that would make them a fire. The nose reports what it is built to report. Something has been oxidized, something has burned. The nose is not equipped to distinguish between a reaction driven by thermal energy and one driven by an atom that has been waiting 300 kilometers for a partner. There is at least one supporting line of evidence that comes from an unlikely direction. In 2008, NASA contracted a fragrance chemist named Stephen Pierce to synthesize an approximation of the smell for use in ground training. The reasoning being that astronauts should not encounter a genuinely novel sensory experience for the first time during a mission. Pierce worked from crew descriptions rather than from a sample, and the result was inevitably an interpretation rather than a reconstruction. But the project surfaced a useful detail. The descriptions were specific and consistent enough to work from. Crews were not groping for words, they were reporting the same thing. The picture is complicated slightly by another candidate mechanism, which may contribute alongside the atomic oxygen chemistry, or may account for a portion of it. The station is a spacecraft, and spacecraft vent things. Thrusters fire using hydrazine or its derivatives. Ammonia circulates in the external thermal control loops. Water sublimates from cooling systems. Some fraction of this material recondenses on external surfaces, particularly the cold ones, and comes back inside with the suit. Hydrazine has a sharp odor of its own, and a suit that has passed near a recently fired thruster may carry traces. The crews are aware of this. There are procedures specifically designed to bake out suits before they are brought fully into the habitable volume, precisely because hydrazine contamination is a genuine toxicological concern rather than an olfactory curiosity. But the timing argues that hydrazine is not the main story. The smell appears reliably after every extravehicular activity, regardless of proximity to thruster plumes. It is not associated with particular operations. It is associated with having been outside. There is a version of this phenomenon that operates on a completely different scale and provides an interesting sideways confirmation. Astronomers studying the interstellar medium, the thin material between stars, have identified a substantial population of polycyclic aromatic hydrocarbons in molecular clouds throughout the galaxy. These are the same class of compound implicated in the airlock smell. They form in the outflows of dying stars, drift for millions of years, and accumulate in the clouds from which new stars condense. Whether the human nose would register a dense interstellar cloud as smelling like a barbecue is an unanswerable question, since no nose could survive the exposure and the density is far too low for detection anyway. But the chemistry is not local. The compounds that give the airlock its character are among the most abundant complex molecules in the galaxy. What the smell demonstrates most clearly is a principle that recurs throughout this subject. The human sensory system, evolved entirely within one atmosphere at one gravity, does not stop working outside those conditions. It keeps reporting. It applies its terrestrial interpretive framework to inputs that framework was never built for, and it produces perceptions that are, in a strict sense, wrong, nothing burned, while being, in a mechanistic sense, exactly right. Something was oxidized. The report is accurate. Only the inferred cause is mistaken. The retina does the same thing with cosmic rays. The nose does it with atomic oxygen. And in 1962, in a small capsule over the Pacific, a pilot's eyes did it with something drifting outside his window at dawn. A phenomenon that would take the better part of a decade to explain, and that began with a transmission nobody on the ground quite knew how to log. The transmission came at about the 48th minute of the flight. John Glenn, in a capsule barely large enough to sit in, coming out of the first orbital night of the American space program, reported that he was inside a large mass of very small particles that were brilliantly lit and appeared to be luminous. He said they were yellowish-green. He estimated their separation at a few feet, their size at perhaps 1/100th of an inch, and their motion relative to the capsule at a few miles per hour. They swirled past the window in enormous numbers. He asked whether anyone on the ground had any information about them, and the answer was no. The value of that transmission lies almost entirely in its texture. Glenn was a Marine aviator with 149 combat missions and a career as a test pilot behind him, and the report reads exactly like a test pilot's report. Quantity, size, spacing, color, relative velocity, followed by a request for information rather than an interpretation. He offered the word fireflies almost apologetically as a placeholder. Then he did the useful thing and kept watching, and reported them again at the next sunrise and again at the third. 3 orbits, 3 dawns, 3 occurrences of the same phenomenon at the same point in the cycle. That timing was the first real clue, and it went underexploited at the time because the more dramatic feature of the observation was the apparent self-luminosity. Glenn said they seemed to glow rather than reflect. This is the detail that pulled the account into places its author never intended it to go, and it is worth resolving before anything else because it is not a property of the particles at all. It is a property of looking at things against a black sky. Human brightness perception is comparative rather than absolute. The eye does not measure photons in any way the conscious mind can access. It measures contrast, and it constructs an interpretation from the ratio between an object and its surroundings. On Earth, a lit object sits in a scene. There is a sky behind it, ground beneath it, other lit objects nearby, all providing a reference against which the brain can judge whether something is emitting light or merely receiving it. In orbit, at night, through a small window, there is no scene. There is a bright thing, and there is nothing. The ratio approaches infinity, and the visual system resolves the ambiguity the only way it can. The object is producing its own light because nothing else in view could be producing it. Every astronaut who has looked at a sunlit object against the orbital night has reported the same impression. It is not an error of observation. It is the correct output of a system operating on inputs it was never designed to receive, which is by now a familiar theme. The second clue was in the relative velocity, and this one is more subtle than it appears. Glenn was traveling at roughly 7,800 meters per second. The particles were moving past him at walking pace. For that to be true of anything in the vicinity, that thing must also be traveling at 7,800 meters per second in nearly the same direction, in nearly the same orbit. There is no mechanism by which a cloud of independent objects would happen to occupy Glenn's orbital parameters to within a few meters per second, unless those objects had been placed there, and only one thing in the vicinity was in a position to place them. Scott Carpenter demonstrated this 3 months later, and did it by accident. On Aurora 7 in May of 1962, Carpenter encountered the same particles at the same point in the orbit. At some moment he struck the inside of the hatch. Accounts differ on whether this was deliberate experimentation or an incidental bump, and a fresh shower of particles peeled away from the capsule and joined the cloud. He did it again. It worked again. The particles were coming from the spacecraft. He radioed the result down, and the phrase that entered the folklore of the program was his report that he had the fireflies too, and knew where they came from. The mechanism, once the source was identified, follows from thermal physics that is fully understood and still slightly startling in its magnitude. An object in low Earth orbit is a thermal system with only one way to lose heat. There is no air to conduct into, no fluid to convect through. Radiation is the sole channel. During the sunlit portion of an orbit, the spacecraft's exterior absorbs solar flux, and its skin temperature climbs. When it crosses the terminator into the planet's shadow, the input stops instantly. Not gradually, as at a terrestrial sunset, but in the span of a few seconds. While the radiative loss continues unabated into a sky whose effective temperature is a few degrees above absolute zero. The exterior temperature falls hard. On a small capsule, surfaces can swing across a range exceeding 200 degrees Celsius between the sunlit and shadowed halves of a 90-minute orbit, and the transition at each terminator crossing takes only minutes. Every crewed spacecraft leaks water. This is not a defect. It is a design feature and an unavoidable consequence of having humans inside. Mercury used steam vented from a heat exchanger to reject cabin heat. The capsule carried condensate from human respiration and perspiration, and any environmental control system that removes humidity from air must eventually put that water somewhere. Some of it goes overboard. Once outside, water vapor in vacuum does not condense into droplets. The pressure is far too low for liquid to exist. It deposits, passing directly from vapor to solid on any surface cold enough to receive it. And after 45 minutes in the planet's shadow, the capsule's skin is very cold indeed. So through every orbital night, A thin frost accumulates on the exterior. Not a visible rime necessarily, a layer measured in microns forming in the crevices around the hatch, along the seams, on the shaded flat surfaces, wherever the local geometry favors deposition. Then the sun comes up, and it comes up in seconds. The metal skin heats rapidly. Ice heats too, but ice and steel have different coefficients of thermal expansion, which means the substrate beneath the frost layer grows faster than the frost layer itself. The bond fails. Simultaneously, the ice at the interface begins to sublimate, passing straight back to vapor. And the vapor generated beneath a flake pushes it away from the surface with a small, gentle impulse. The result is a shedding event. Thousands of ice crystals, released from every frosted surface at once, at relative velocities of centimeters per second, entering orbits nearly identical to the vehicle's own. They then do exactly what Glenn described. They drift. They swirl because they were released from surfaces with different orientations and different local thermal histories, and because the capsule itself was slowly rotating. And they catch the light, but at sunrise, with the sun near the horizon, they are illuminated at a grazing angle, and small ice crystals scatter light with strong forward and near-forward preference. This is why they appeared at dawn and faded as the sun climbed. Two things happened at once. The scattering geometry became less favorable as the illumination angle changed, and the crystals themselves sublimated away in direct sunlight, gone within minutes of the thing that revealed them. 3 sunrises, 3 sheddings, 3 clouds. The pattern was in the data from the first orbit. There is a coda to this that shows how thoroughly the explanation was confirmed by simply doing more spaceflight. Every subsequent program encountered the same thing at larger scale with better cameras. Gemini crews saw it. Apollo saw it. Shuttle crews called them snowflakes and reported them constantly, and shuttle era video shows them clearly. Slow, tumbling, obviously irregular chips of ice drifting out of the payload bay and away. The station sheds them today. Wally Schirra on Sigma 7 coined a joke about a new constellation formed by the flash-frozen contents of a urine dump. A genuine phenomenon, since dumped liquid in vacuum boils and freezes at the same time, producing a cloud of ice particles that has on occasion been mistaken from the ground for something more interesting. Glenn himself never wavered on any of this. He reported what he saw, and when the explanation arrived, he accepted it, and he spent the rest of a long public life patiently telling people that the fireflies were ice off the side of his spacecraft. The account nonetheless became foundational in a literature he had no interest in, mostly because the phrase brilliantly lit up like they are luminescent, extracted from a transcript and stripped of the perceptual context, sounds like a claim rather than a description. Which brings out the actual lesson of Friendship 7, and it is a lesson about instruments rather than about ice. Glenn's eyes worked perfectly. Every element of his report was accurate. The particles were there, they were that size, that color, that far apart, moving at that speed. The single inference he got wrong, that they were emitting light, was not an error of attention or of honesty. It was a structural limitation of a visual system that requires context to compute brightness, and had been placed somewhere without any. The same limitation runs through every account in this subject. An observer in orbit has no depth cues, no size references, no atmospheric perspective to indicate distance, no horizon to establish scale. Objects near the vehicle and objects a kilometer away look identical. This is not a failure of the observers. It is a property of the environment, and it is why so many of these reports required a second observation, or a camera, or an accidental blow to a hatch before they could be resolved. But the environment that strips those cues away also delivers something no ground observer ever receives. Glenn's particles appeared at sunrise. He witnessed 3 of them in under 5 hours, and the thing that made them visible, that sudden, near-instantaneous arrival of the sun, is itself among the more revealing sights available from orbit because of what it illuminates on its way in. The sun rises 16 times a day on the International Space Station, and each rise takes about 6 seconds from first light to full disk. That figure is the beginning of the interesting part, not the end of it, because 6 seconds is not a poetic exaggeration. It falls directly out of the geometry. The station moves at roughly 7.7 kilometers per second, along a track that carries it around the planet in about 92 minutes. The Sun, seen from that distance, subtends about half a degree of arc, the same apparent size it has from the ground, since 400 kilometers is nothing against 150 million. For the station's motion to carry the Sun's full disk up from behind the limb of the Earth, the vehicle must travel far enough along its orbit to sweep through that half degree of angle. At its orbital rate, that takes a handful of seconds. There is no atmospheric refraction to stretch it out, no scattering to announce it in advance, no long, slow lifting of light through kilometers of air. There is darkness, then a line, then the Sun. What crews consistently describe, though, is not the Sun. It is the band. In the moments before the disk clears the horizon, the sunlight passes tangentially through the atmosphere, entering the air at a grazing angle, traveling hundreds of kilometers through progressively denser layers, and emerging toward the observer with everything the air has done to it written into its color. This is the same physics that reddens a terrestrial sunset, operating over a far longer path. Short wavelengths scatter out. What survives the passage is red, then orange, then a narrow yellow-white core where the light is fresh from the source. Above that, the scattered blue. Above that, a violet-tinged transition that crews find difficult to name. And then black. The whole structure, from the surface to the top of the visible atmosphere, occupies a band on the limb that is thin enough to cover with a thumbnail at arm's length. This is the observation that recurs in astronaut accounts more than any other, and it recurs because it is not a feeling. It is a measurement they are making with their own eyes and reporting accurately. The numbers behind it are worth laying out, because they are counterintuitive even to people who know them. The Earth's radius is about 6,371 kilometers. The troposphere, the layer containing essentially all weather, nearly all clouds, and the overwhelming majority of the atmosphere's mass, extends about 12 kilometers at the equator and less at the poles. The stratosphere runs to about 50. Above 80 kilometers, the air is thin enough that the region is functionally space for most purposes. If the planet were reduced to the size of a common desk globe, the entire breathable layer would be thinner than the varnish on its surface. If it were an apple, the atmosphere would be shallower than the skin. Crews see this ratio directly without having to be told. The band is not a symbol of fragility. It is the actual thickness of the actual atmosphere, viewed edge-on from a position where the comparison to the planet beneath is unavoidable. Michael Collins, orbiting alone while his crewmates were on the lunar surface, remarked on the color of the Earth's limb. Sally Ride described being struck less by the beauty of the planet than by the thinness of the line around it. The reaction is nearly universal among people who fly, and it is worth being precise about why. It is not that the view is emotionally affecting, though it is. It is that the view supplies a quantitative fact that no diagram delivers. The system supporting every organism that has ever lived is a film. The band also has structure, and the structure is legible if you know what to look for. The lowest layers closest to the surface carry the reds and the aerosols. Dust lifted from deserts, salt from breaking waves, sulfate from volcanoes, and from combustion, water droplets. This is where the atmosphere is dirty in the technical sense, loaded with particles large enough to scatter light without much wavelength preference, which is why the lowest few kilometers of the limb often appear as a muddier, warmer color than the clean blue above. Higher in the stratosphere, the air is dry and stable and stratified, hence the name. And the limb view shows this as distinct horizontal layering. After large volcanic eruptions, this layering becomes dramatically more visible from orbit. Sulfur dioxide injected above the tropopause converts to sulfate aerosol and spreads into a thin global veil, and crews flying in the years after a major eruption have photographed the resulting bands on the limb as clearly defined stripes. The eruption of Pinatubo in 1991 put enough material into the stratosphere to be tracked this way for years, and to lower the planet's mean surface temperature by a measurable fraction of a degree. Higher still, near 80 kilometers, sits the coldest region of the entire atmosphere. The mesopause, where temperatures drop below 140 Kelvin, colder than anywhere on the surface of Antarctica by a wide margin. And there, in a layer of air so thin it is a hard vacuum by laboratory standards, clouds form. Noctilucent clouds, ice crystals condensing on meteoric dust, requiring almost no water vapor because there is almost no anything, illuminated by sunlight after the surface below has gone dark. From the ground they appear at high latitudes on summer nights as pale electric blue filaments. From orbit, crews see them as a distinct shelf sitting above the ordinary weather, at an altitude no aircraft can reach, near the boundary where the atmosphere stops being an atmosphere. They are also relatively new. The first documented observations date to the 1880s, a few years after Krakatoa, and their frequency and brightness appear to have increased since. One proposed mechanism involves methane. It rises, oxidizes in the upper atmosphere, and produces water vapor in a region that has almost none. More methane below could mean more ice above. The correlation is suggestive rather than settled, but it makes the point that the highest, thinnest, most remote layer of the sky is not isolated from what happens at the bottom of it. All of this is visible in 6 seconds, 16 times a day, and then the terminator passes and the geometry inverts. The terminator itself is the other thing crews find unexpectedly informative. From the ground, the boundary between day and night is a temporal event. It arrives, it takes time. It is experienced rather than seen. From orbit, it is a place. It is a line drawn across the planet's surface, running from pole to pole, and the station crosses it at 8 kilometers per second, which means the line sweeps across the ground beneath, at a rate that varies with latitude but is, near the equator, roughly the speed of sound multiplied by a factor of a few. Ahead of the vehicle, the world is lit. Behind it, night. The crew passes from one to the other in the time it takes to look up, and the two halves of the orbit look nothing alike. On the day side, the planet is overwhelming. Ocean color grading from turquoise over shallow banks to a blue so dark, it reads as ink. Cloud systems with visible three-dimensional structure and shadows, river deltas, the pale scars of dry lake beds, the geometric intrusion of agriculture. Almost no artificial structure is individually resolvable to the eye at 400 kilometers, whatever the persistent claim about walls suggests. What is visible is pattern, the rectangular grid of surveyed farmland, the plume of sediment where a river meets the sea, the straight line of a highway cutting across terrain that has no straight lines of its own. On the night side, the planet largely disappears and the human presence takes over. Cities appear as nodes of light connected by threads. The threads are roads. The pattern is legible as economics and geography. Dense webs across Europe and eastern North America, the sharp bright line of the Nile with darkness on either side, the coastal necklaces of Asia, entire ocean basins with nothing at all except, occasionally, a scattered constellation of fishing fleets running lights so bright they are visible from orbit. Gas flares burn in oil fields. Lightning propagates through cloud systems in slow, silent pulses, illuminating the tops of thunderstorms from within, so that a squall line 500 kilometers long flickers like something conducting. Between the two, at the terminator, is the transitional zone crews often single out. The region where the sun is below the local horizon at the surface but still illuminating the upper atmosphere. Long shadows stretch from mountain ranges. Cloud tops catch light while the ground beneath is dark. The three-dimensionality of the atmosphere, invisible at noon, becomes suddenly obvious. And then it passes, and there is 45 minutes of night, and then it happens again. 16 times daily for months. The repetition is itself a physiological problem, and one that the station's designers had to address deliberately. The human circadian system entrains primarily to light, and specifically to blue-weighted light striking specialized retinal cells that have nothing to do with vision. Intrinsically photosensitive ganglion cells which report to the hypothalamus rather than the visual cortex and do not care whether you are consciously looking. A 92-minute light cycle provides that system with an input it cannot use. Left uncorrected, sleep architecture degrades. Crews take longer to fall asleep, wake more often, and accumulate a deficit that shows up in reaction time and error rates. The station now runs on Greenwich Mean Time with a scheduled artificial day, and the lighting has been progressively upgraded to allow spectral tuning. Bluer during the working day, warmer in the evening. Because the sunrise outside the window is, from a biological standpoint, noise. Which is a strange thing to conclude about a sunrise. But it captures something about the orbital environment generally. Every phenomenon there is simultaneously a spectacle and an engineering constraint, and the crews are the only instrument capable of registering both at once. And on the night side, in that 45 minutes of darkness, there is a class of event that the atmosphere hides from anyone standing beneath it. Storms do not only discharge downward. Above the tops of the largest thunderstorms, something reaches upward, and it was dismissed as pilot error for the better part of a century. The reports came from pilots first, and they were not believed. For most of the 20th century, air crews flying near large thunderstorms at night occasionally described something above the clouds, a flicker, a column of reddish light standing over a storm top, lasting an instant, gone before it could be pointed at. The observations went into no formal record because there was no formal category to put them in, and because the professional cost of reporting them was real. Lightning goes down. Everyone knew this. A pilot who claimed otherwise was describing an afterimage, a reflection off the windscreen. Fatigue. CTR Wilson had predicted them in 1925. Wilson was not a marginal figure. He built the cloud chamber, won a Nobel Prize for it, and spent much of his career on atmospheric electricity. His argument was straightforward electrostatics. A thundercloud separates charge, building a dipole with typically negative charge low and positive high. When a lightning stroke removes a large quantity of charge from the cloud in a few milliseconds, the electric field above the cloud does not simply relax. It changes suddenly and enormously, and it extends upward. Field strength required for electrical breakdown falls with air density, and air density falls exponentially with altitude. Somewhere high enough, Wilson reasoned, the field from a large stroke must exceed the local breakdown threshold, and the air must respond. The prediction sat for 64 years. In July of 1989, a group at the University of Minnesota was testing a low-light television camera, pointing it out at the sky while calibrating for a rocket campaign. They were not looking for anything. 2 frames of video captured 2 enormous columns of light standing above a distant storm, extending tens of kilometers into the atmosphere. The recording was accidental and unambiguous, and it ended the argument in the time it took to play the tape. What followed was a decade of instrumentation, much of it from orbit, and the discovery that the region above thunderstorms is not empty. It is a zone of routine electrical activity that the atmosphere itself had been hiding, because the same clouds producing the phenomena stand between them and any observer on the ground. The most common of these is the sprite, and the name was chosen deliberately to avoid committing to a mechanism. A placeholder that stuck. A sprite is a large-scale electrical discharge in the mesosphere, triggered by a lightning stroke below it, and its structure is unlike anything in the lower atmosphere. It occupies the region between roughly 40 and 90 kilometers of altitude. Its color is red at the top, fading toward blue in tendrils below. It lasts a few milliseconds, long enough for the human eye to register as a flicker, not long enough to examine. And a large one may span 40 kilometers vertically and 20 horizontally, which makes it, by volume, one of the largest single electrical events on the planet. The color is the diagnostic. It comes from molecular nitrogen, which makes up most of the atmosphere at that altitude, and which, when its molecules are excited by free electrons and then relax, emits preferentially in a red band. This is the same emission that gives the highest auroras their red color, produced by the same molecule under similar conditions. The blue tendrils below come from ionized nitrogen, requiring more energy per event, occurring where the air is denser and the collisions harder. The vertical color gradient in a sprite is therefore a direct readout of atmospheric density along its length. Red where the air is thin, blue where it thickens. Sprites are also almost exclusively associated with positive cloud-to-ground strokes, which are the minority, perhaps 10% of lightning, but which transfer far more charge. The mechanism is precisely Wilson's. A large positive stroke abruptly removes charge, The field above the storm jumps, electrons in the mesosphere accelerate, and the air breaks down over a region tens of kilometers across. The delay between the stroke and the sprite is a few milliseconds, which is the time required for the field change to propagate upward and for the avalanche to develop. Then there is the blue jet, which is a different animal entirely. Jets do not respond to a stroke below them. They emerge from the storm top itself, a narrow cone of blue light climbing from around 15 kilometers to 40 or 50, moving at something like 100 kilometers per second, slow enough that video captures the propagation rather than a static image. They appear to be a discharge escaping upward from the cloud into clear air, and their blue color reflects the denser atmosphere they traverse. Gigantic jets, a rarer variant, can bridge the entire gap from the cloud top to the ionosphere, completing an electrical connection between a thunderstorm and the conducting layer of the upper atmosphere directly. When that happens, the storm is briefly wired to the ionosphere, and there are elves, which are the fastest and the strangest. An elf is a ring of light expanding outward at the speed of light in a thin sheet near 95 kilometers of altitude. It lasts under a millisecond. Its geometry is not a discharge at all. When a lightning stroke occurs, it radiates an electromagnetic pulse in all directions, and the portion traveling upward reaches the base of the ionosphere and dumps energy into free electrons there, exciting nitrogen across a disk that can exceed 300 kilometers in diameter. It is not the electricity arriving. It is the radio pulse from the electricity, and the light traces the wavefront. An elf is what you get when you illuminate a ceiling with a flash from below. The station is unusually well placed to study these because, from 400 kilometers up, an observer is looking down at the storm tops rather than through them. The ISS has flown dedicated instrumentation for this, most substantially the Atmosphere Space Interactions Monitor, mounted on the Columbus module, which combines optical cameras with X-ray and gamma-ray detectors specifically to catch these events from above. Crews have also photographed them by hand, in the ordinary course of pointing a camera at the night side and letting the exposure run. The gamma-ray detectors are on that instrument for a reason, and the reason is the least expected result to come out of this field. In the 1990s, the Compton Gamma Ray Observatory, designed to look outward at the most violent objects in the universe, began registering brief bursts of gamma radiation coming from below. From the Earth. These are now called terrestrial gamma ray flashes, and they last well under a millisecond, and they originate in the upper regions of thunderstorms. The energies involved reach into the tens of millions of electron volts, which is not chemistry and not weather in any ordinary sense. It is nuclear-scale radiation produced by a cloud. The mechanism appears to be relativistic runaway electron avalanche. Under a sufficiently strong field, a free electron accelerates faster than it loses energy to collisions, and it keeps accelerating, reaching relativistic velocity. When it eventually strikes a nucleus, it decelerates hard and radiates the difference as a high-energy photon, Bremsstrahlung, braking radiation, the same process that generates X-rays in a medical machine. One electron produces more free electrons, which run away in turn. The avalanche grows exponentially. The output is a beam of gamma rays fired upward out of the storm. There is a consequence of this that is still being worked out. Those gamma rays are energetic enough to induce photonuclear reactions in atmospheric nitrogen, knocking a neutron out of the nucleus. That means thunderstorms produce neutrons. It also means they produce positrons, the antimatter counterpart of the electron, as a decay product of the isotopes left behind. Fermi, a gamma-ray satellite, detected a signature consistent with a beam of positrons traveling up a magnetic field line from a storm and annihilating on the far side of the planet. Ordinary weather on this planet makes antimatter. Not much and not for long, but the process is routine and the detections are unambiguous. The obvious question, whether an aircraft passing through one of these would matter, has been studied without a clean answer. The dose from a single flash to a plane in exactly the wrong place could be non-trivial, but the events are brief, localized, and rare relative to the volume of sky, and no confirmed case exists. The more consequential point is what it says about the atmosphere itself. The region between the storm tops and the ionosphere, which was for most of scientific history simply the space where the weather stopped, is electrically active, structured, and coupled to the layer above it. Charge moves between the troposphere and the ionosphere constantly. The global electrical circuit is real, and thunderstorms are its generators. None of this was visible from below. All of it required either an accident with a low-light camera or a vantage point above the clouds. And it is a reminder that the sky has a vertical dimension that ground-based observation systematically flattens. That what looks like weather from underneath is the bottom edge of something with structure all the way up. That structure does not stop at 95 kilometers. It continues, and near the poles it becomes something a person can see with the unaided eye, from above, at an altitude where the phenomenon is not overhead but underfoot. Ask anyone who has watched an aurora from the ground where it is, and the answer will be up. It is in the sky. It hangs above the observer, a curtain draped across the top of the world, and the visual system reports it as a ceiling because that is where it appears, spread across the dome, with no reference to indicate otherwise. The impression is so consistent that early attempts to measure the altitude of the aurora produced estimates ranging from a few kilometers to several hundred, depending entirely on which unreliable assumption the observer happened to make. From orbit, the geometry resolves itself immediately, and it resolves in a way that inverts every intuition the ground view supplies. The station flies at roughly 400 kilometers. The aurora's most common emission region begins around 100 kilometers of altitude and extends upward, with typical structure through the range of 100 to 300 kilometers, and occasional features reaching 400 or beyond. This places the cruise inside the vertical extent of the phenomenon, rather than beneath it. On a typical pass over the auroral oval, the lights are below the vehicle. A green sheet lying across the darkened planet, seen from above, with the curtains extending upward toward the observer and sometimes past them. Crews have described flying through the tops of active auroral structures. This is not a figure of speech. During geomagnetically disturbed periods, when the oval expands equatorward and the emission region extends higher, the station's orbital path intersects the upper portion of the emitting volume. There is nothing to feel. The particle density involved is negligible against the vehicle's mass, and the station's own atmosphere is unaffected. But the view from the cupola shows the structure passing beside and beneath the windows rather than overhead. What the crews are seeing is worth stating precisely, because the popular description of the aurora as solar wind hitting the atmosphere is a compression of the mechanism so severe that it discards the interesting parts. The sun continuously emits a plasma of protons and electrons, moving outward at typically 400 kilometers per second, and occasionally much faster. This plasma carries the sun's magnetic field with it, frozen in, because a conducting fluid and a magnetic field cannot easily move through each other. When this magnetized wind reaches the Earth, it encounters the planet's own magnetic field, and the interaction is not a collision, it is a magnetic one. The Earth's field, generated by convection in the liquid iron outer core, is roughly a dipole close in, but it does not remain one under load. The solar wind compresses it on the day side, pushing the boundary into roughly 10 Earth radii, and stretches it on the night side into a tail extending hundreds of Earth radii downstream, past the Moon's orbit, in a long structure that the Moon passes through every month. The result is not a shield in the sense of a wall. It is a deflector, and it leaks. The leaking is the point. When the solar wind's embedded magnetic field is oriented southward, anti-parallel to the Earth's field at the dayside boundary, the two fields can undergo magnetic reconnection. Field lines break and reconnect across the boundary, which is a process that has no everyday analog and which converts stored magnetic energy into particle kinetic energy with considerable efficiency. Reconnected field lines, now connected at one end to the Earth and at the other to the solar wind, are dragged over the poles and into the magnetotail. There they accumulate, stretching the tail, storing energy. The tail cannot store it indefinitely. When the stress exceeds what the configuration can hold, reconnection occurs again, this time in the tail, at a point roughly 20 to 30 Earth radii downstream, and the stored energy releases. Plasma is accelerated in both directions along the field. Some goes outward, lost. Some goes inward, funneled along the converging field lines toward the polar regions, accelerating as it goes, entering the atmosphere at high latitude with energies of several thousand electron volts. This is the substorm, and it is what makes the aurora suddenly brighten and begin to move. The energy in an auroral display did not come from the sun a few minutes earlier. It was extracted from the solar wind, stored in the magnetotail for perhaps half an hour to an hour, and then released. The display is the discharge of a capacitor whose plates are the size of a planet. When those accelerated electrons reach the upper atmosphere, they collide with atoms and molecules, excite them, and the excited species relax by emitting photons. The colors are not aesthetic choices. They are a direct readout of composition and altitude, and they encode more information than any other visual feature discussed here. The dominant green, at 557.7 nanometers, comes from atomic oxygen. This emission is what physicists call forbidden. The transition violates the ordinary selection rules of quantum mechanics, and an excited oxygen atom in that state will wait, on average, about 3/4 of a second before emitting. 3/4 of a second is an eternity at atomic timescales. In any denser gas, the atom would collide with something and give up its energy without emitting, a process called quenching. The green aurora is therefore only possible in a region where the atmosphere is thin enough that an atom can go 3/4 of a second without being touched. That condition holds above roughly 95 kilometers. Below that, the green does not appear. The lower edge of the green aurora is a direct visual marker of the altitude where the air becomes thin enough to permit a forbidden transition. The red, at 630 nanometers, is also atomic oxygen, and it is a still more extreme case. The lifetime of that excited state is around 110 seconds, nearly 2 minutes. This emission can only escape at altitudes above roughly 200 kilometers, where collisions are rare enough that an atom can remain excited for that long undisturbed. The red aurora crowns the green because it physically cannot exist lower. When a display shows red above green, it is displaying the density gradient of the atmosphere as a color gradient. The blues and violets come from ionized molecular nitrogen, and they require the most energetic incoming particles, the ones that penetrate deepest, below 100 kilometers, into air dense enough to matter. Their appearance signals a more energetic event. None of this is legible from the ground with anything like the same clarity because the ground observer is looking up through the emitting volume and integrating all the altitudes together. From orbit, looking down and across, the layering separates. Crews photograph the limb during auroral activity, and the vertical structure is explicit. A green sheet with a sharp lower boundary sitting exactly where physics says the quenching stops. Red diffusing above it, the whole assembly standing on the darkened planet like something drawn in a diagram. The oval itself is the other thing the orbital view corrects. From the ground, the aurora is a local phenomenon at the observer's location. From orbit, crossing the high latitudes, it is obviously a ring, a permanent, continuous circle centered not on the geographic pole but on the magnetic one, offset by several degrees, with a diameter that expands and contracts according to how much energy is being dumped into the system. In quiet conditions, the ring is small and sits over the far north. During a strong geomagnetic storm, it swells southward, which is why auroras occasionally appear over latitudes that never see them otherwise. The ring exists at all times, on both hemispheres simultaneously, and the two are nearly mirror images of each other because the particles are traveling along the same field lines to both ends. That mirroring has been observed directly. Simultaneous imaging of the northern and southern ovals shows conjugate features, a spiral in one hemisphere with a counterpart in the other, appearing at the magnetically corresponding location. The displays are two ends of the same structure, separated by the entire planet. There is a final detail that pulls the whole thing into perspective. The energy involved in a strong auroral substorm is on the order of 100 billion watts, sustained for tens of minutes. That is a substantial fraction of global electrical generating capacity, delivered continuously into the upper atmosphere over the polar regions every time the tail unloads. It heats the thermosphere, which expands, which increases atmospheric drag on satellites, which is why geomagnetic storms require orbital maintenance and why the station's reboost schedule is sensitive to solar activity. The station is inside the system it is observing, and the same field that produces the aurora at the poles has a weakness elsewhere, a region where it dips low enough to matter and where the crew's laptops crash on schedule. But before that, in 1996, a shuttle crew deployed a satellite on a 20-kilometer tether, and the tether broke, and the camera kept running. The mission was STS-75, and the experiment was not fringe science. The tethered satellite system was a serious piece of physics, flown twice, built on a principle that is taught in introductory electromagnetism and rarely demonstrated at scale. Move a conductor through a magnetic field and you generate a voltage. The shuttle was moving through the Earth's magnetic field at nearly 8 kilometers per second. Extend a conductive wire 20 kilometers from the orbiter, and the wire becomes a generator. The field induces a potential difference along its length, and if the circuit can be closed through the surrounding plasma, current flows. The ionosphere at that altitude is conductive enough to serve as the return path. The satellite at the far end collects electrons. The orbiter emits them back through an electron gun. A closed loop, 20 kilometers across, with the ionosphere as the wire you cannot see. The system worked. During deployment, before anything went wrong, the tether generated over 3,000 volts and drove currents substantially higher than the models predicted, which was itself a result worth having, since it indicated the ionosphere accepted current more readily than the theory assumed. Then, at a deployed length of about 19.5 kilometers, the tether broke. The cause was traced to an electrical arc, a flaw in the insulation, a discharge through it, and the tether burned through under a current it was never meant to carry at that point. The satellite departed, still attached to 20 kilometers of severed cable, drifting away from the orbiter and slowly receding. The crew filmed it. The camera used was a black and white low-light unit, sensitive into the near ultraviolet, which matters enormously for what follows. And the footage ran for some time as the tether receded into the distance against the dark. In that footage, objects appear. They are circular. They have a visible darker region near the center, giving them the look of a disc with a notch or a hole. They move with apparent purpose, drifting across the frame, and some of them pass behind the tether, or appear to. Their sizes vary. They come and go. In some sequences, there are dozens. The footage entered public circulation quickly, and the interpretation attached to it was immediate and durable. Large objects, kilometers across, maneuvering in the vicinity of the orbiter. The size claim was derived by assuming the objects were at the tether's distance, the tether being the only object in frame whose dimensions were known. If a disk appears half as wide as a tether that is at a known range, and if the disk is at that same range, then the disk's diameter follows from simple trigonometry. The arithmetic is correct. The assumption is the problem. Consider what the visual system and the camera share here, and what neither has. The scene contains exactly two things: a tether and darkness. There is no atmosphere to fade distant objects, no ground plane to establish position, no occlusion by known landmarks, no stereo baseline. A single camera in a vacuum against a black background has precisely no information about the distance to any object it sees. None. This is not a limitation of that particular camera. It is a mathematical property of monocular imaging without depth cues. An object's angular size is the ratio of its physical size to its distance, and a single measurement of angular size determines neither term. A 10-meter object at 1 kilometer and a 10-centimeter object at 10 meters produce identical images. So the question becomes, what is actually there? And the answer is that the volume immediately around a shuttle orbiter is far from empty. Every crewed spacecraft is surrounded by its own debris cloud. Ice sheds from surfaces as established. Thruster firings deposit unburned propellant droplets that freeze. insulation flakes, paint chips. Material shakes loose from the payload bay every time something moves. During tether operations specifically, the deployment mechanism was actively shedding material, and the tether brake itself, an electrical arc severing a cable under tension, would have produced a substantial quantity of fragments. Insulation, conductor, whatever was near the arc. The orbiter also dumps water and vents gases, and both freeze on release. This material sits within meters to tens of meters of the vehicle, moving at relative velocities of centimeters per second in orbits that keep pace. It is exactly the population Glenn saw and Carpenter shook loose by hand. Now the discs. Debris of this kind is irregular. Flakes, chips, tumbling fragments with no particular shape. So why do the objects in the footage appear circular, and why do they have that distinctive central darkening? Because they are out of focus. A point of light imaged by a lens focused at a different distance does not appear as a point. It appears as a disc, the cross-section of the light cone at the sensor plane, called the circle of confusion. Its shape is determined by the aperture, not by the object. Any small, bright thing of any shape whatsoever that lies well outside the focal distance will render as a disc. Photographers exploit this deliberately and call it bokeh. Every out-of-focus streetlight in every night photograph ever taken is the same artifact. The central darkening follows from the specific optics involved. Catadioptric lenses, mirror lenses which use a folded light path with a secondary mirror mounted in the center of the aperture, produce out-of-focus highlights shaped like annuli, bright rings with dark centers because the secondary mirror obstructs the middle of the light cone. The signature is unmistakable to anyone who has used one, and it is present in the footage. The objects look like discs with holes because they are images of the aperture, and the aperture had a hole in it. The apparent motion resolves the same way. Debris at a few meters, moving at a few centimeters per second, crosses a narrow field of view rapidly in angular terms. Debris at greater distance crosses slowly. Mixing the two populations in one frame produces exactly what the footage shows. Some objects moving fast, some slow, some apparently changing direction as the orbiter's own rotation carries the camera. Nothing in the footage requires anything to be more than a few meters away, and everything in it is consistent with the debris cloud that every shuttle mission carried. The occlusion claim that objects pass behind the tether is the one point of genuine substance in the argument, and it does not survive examination either. The tether at that range was a thin, bright line near the resolution limit of the sensor. An out-of-focus disc drifting across it does not neatly occlude or fail to occlude. The two blend, and the eye interprets the result according to expectation. Frame-by-frame analysis by multiple parties found no case in which an object unambiguously passed behind the tether, and the tether's own brightness. It was near ultraviolet bright, glowing from the plasma interaction, makes the determination harder rather than easier. NASA's position has been consistent and, notably, was reached by the imaging specialists rather than by a public affairs office. The objects are debris and ice near the camera, rendered as disks by defocus. The tether brake generated a debris field, and the camera photographed it from a few meters away with the focus set at infinity. What makes this episode worth including is not the resolution, which is unremarkable. It is what it demonstrates about the entire category of orbital observation. Every account in this subject was made by an observer without depth cues. Glenn could not tell how far his particles were. The tether camera could not tell how far its disks were. A crew member seeing something out a window has no atmospheric perspective, no size reference, no ground plane, no stereo baseline beyond a few centimeters of eye separation, which is useless past about 10 meters. The environment systematically strips out every cue the human visual system evolved to depend on, and then presents objects against a background that provides nothing. The result is that size and distance become unrecoverable, and the mind supplies the missing term. It has to. A percept requires both. So it guesses, and it guesses using terrestrial priors that do not apply, and it produces an experience of a large distant object where the data equally support a small near one. This is not a failure of observation. It is the correct behavior of a system asked to solve an underdetermined problem. The observers were not mistaken about what they saw. They were mistaken about how far away it was, and in that environment, that is not a mistake anyone can avoid without an independent measurement, which is precisely why the resolvable case is resolved. Someone hit a hatch, someone read a plastic track detector, someone identified the aperture shape, and it is why the harder cases stayed hard, including one that arrived not through the eyes at all but through a headset on the far side of the moon where no signal was supposed to reach. The moon is 2,159 miles across, and it is opaque to radio. That single fact structured every Apollo mission that went into lunar orbit. Radio waves at the frequencies used for spacecraft communication travel in straight lines. They do not bend around obstacles of that scale, and they do not pass through 3,400 kilometers of silicate rock. When a spacecraft's orbit carried it behind the moon relative to Earth, the link did not degrade. It ended. Loss of signal was predicted to the second by orbital mechanics, and it arrived on schedule, and for the next roughly 45 minutes, the crew was in a condition no human beings had ever occupied before. Entirely out of contact with the rest of the species, with no possibility of assistance, no telemetry flowing home, and no way to know whether anyone would hear from them again until the geometry brought them back around the limb. Apollo 8 did this first in December of 1968. The most consequential engine burn of the mission, lunar orbit insertion, was scheduled during the blackout, which meant the crew would fire an engine that had to work alone, with the outcome unknown on the ground until acquisition of signal either happened at the predicted time or did not. A late acquisition meant a failed burn. A very late one meant something worse. Mission Control had a clock and nothing else. In May of 1969, Apollo 10 went through that same silence, and something came through it. The mission was the full dress rehearsal. Everything except the landing. Thomas Stafford and Eugene Cernan in the lunar module, John Young alone in the command module, and the two vehicles separated in lunar orbit, while the lunar module descended to within about 15 kilometers of the surface and came back. Behind the moon, cut off from Earth, the two spacecraft could still speak to each other. They had a direct VHF link between them, and it worked because they were within line of sight of one another, even when neither could see home. On that link, the crews heard music. The transcript is direct about it and largely unbothered. Cernan describes a whistling sound. Someone calls it outer space type music. Stafford remarks that it sounds like something from an outer space movie. The tone of the exchange is not alarm, it is the tone of professionals encountering an anomaly and turning it over. They discuss whether anyone will believe them. They agree it is eerie. It goes on for close to an hour, and then it stops, and they come around the limb and get on with the mission. The recordings and transcripts were released in 1973 as part of the ordinary technical documentation of the program. They were not classified, and no effort was made to withhold them. But they were also not promoted because they were, from an engineering standpoint, unremarkable. They surfaced in public consciousness decades later, presented as suppressed material, and the framing did more work than the content, because the explanation was already in print, written by someone with direct knowledge before the transcripts were even released. Michael Collins flew the command module on Apollo 11, 2 months after Apollo 10. In his memoir, published in 1974, he mentions that he had been briefed about the whistling in advance and told exactly what it was: interference between the lunar module's VHF radio and the command modules. He notes with some dryness that had he not been warned, the experience would have scared him considerably. The mechanism is a well-understood property of radio hardware. When two transmitters operate near each other on nearby frequencies and their signals both enter a receiver's front end, the receiver's nonlinear components, the mixers and amplifiers that are essential to how superheterodyne radios function, do not simply add the signals, they multiply them. The output contains not only the original frequencies, but their sums and their differences. This is not a defect. It is the operating principle of every radio receiver built since the 1920s. To tune a station, the receiver deliberately mixes the incoming signal with a locally generated one and works with a difference frequency. The process is called heterodyning, and when it happens on purpose, it is engineering, and when it happens by accident, it is interference. If the difference between two frequencies falls into the audio band, the receiver produces a tone. If the two transmitters are drifting relative to each other, from thermal changes in their oscillators, from Doppler shift as the vehicles move, from power fluctuations, the difference frequency drifts too and the tone slides. Two vehicles maneuvering in lunar orbit, each with a transmitter whose oscillator temperature depends on where the sun is and what the equipment is doing, will produce a difference frequency that wanders continuously. A wandering tone, rising and falling, with no percussive component and no clear source, is what a human auditory system will parse as music. The system is built to find pitch and contour. It will find them in almost anything that has them. Radio operators have heard this sound for a century and call it a heterodyne whistle, and it is the reason two stations on adjacent frequencies produce an audible squeal in an old receiver. What the Apollo 10 crew heard was the same artifact, generated by two radios a few kilometers apart, in a place where the only other thing to listen to was silence. The confirming detail is in the geometry. The interference occurred when the two vehicles were separated and both transmitting. It required two radios. Apollo 10 was the only mission before 11 to have the lunar module operating independently in lunar orbit, which is why the phenomenon appears in that transcript and not in Apollo 8's, where there was one vehicle and no second transmitter to beat against. There is a further layer worth noting, because it explains why the crews found it strange at all rather than simply recognizing it. Interference of this kind is common on Earth and therefore invisible. It happens against a background of other noise, other stations, static, atmospheric crackle. Behind the moon, the VHF link was the only signal in existence. The moon's bulk was blocking every transmitter on Earth, which is to say every artificial radio source in the universe as far as those receivers were concerned. The heterodyne was not one sound among many. It was the only sound, arriving into a silence more complete than any radio operator on Earth has ever experienced. That silence is not a curiosity. It is now among the more valuable pieces of real estate in the solar system. The Earth is radio loud and getting louder. Television broadcasts, FM stations, military radar, cell networks, satellite downlinks, and the switching noise of several billion electronic devices produce a background that saturates the low-frequency spectrum. Below roughly 30 megahertz, the situation is worse still, because the ionosphere, the same conducting layer that makes long-distance shortwave possible, reflects those frequencies. It bounces terrestrial noise back down, and it blocks cosmic signals from getting in. From the surface of the Earth, the low-frequency radio sky is effectively closed. There is a window, and the ionosphere is a shutter across it. The lunar far side removes both problems at once. During lunar night, on the hemisphere permanently turned away from Earth, an antenna sits behind 3,400 kilometers of rock that attenuates terrestrial emission by an enormous factor, with no ionosphere overhead to reflect anything or block anything, and with the sun below the horizon so that solar radio noise is absent as well. It is the quietest location for low-frequency radio astronomy accessible to us, and there is no comparable site anywhere else. What that quiet would allow is a specific and consequential observation. In the era after the cosmic microwave background was emitted, and before the first stars ignited, the universe consisted mostly of neutral hydrogen, dark, structureless, and largely unobservable. That period is called the Dark Ages, and it is the last major gap in the observational record of cosmic history. Neutral hydrogen emits at a wavelength of 21 centimeters, and light from that era has been stretched by cosmic expansion until that emission arrives at frequencies below about 50 megahertz. Precisely the band the ionosphere blocks. Precisely the band terrestrial transmitters fill. Mission concepts have accumulated for years around this, Instruments designed to sit on the far side through the 2-week lunar night, listening for a signal that has been traveling for 13 billion years, are now moving from proposal toward hardware. The reason the location matters is not convenience. It is that the far side is the only place in the accessible universe where the measurement is possible at all. The Apollo 10 crew, in other words, were sitting in the future site of the most sensitive radio observatory anyone has proposed, listening to their own transmitters interfere with each other, and describing it as music because the human auditory system, given a wandering tone and nothing else, will do exactly that. The pattern by now is familiar. A sense evolved for one environment, placed in another, reporting accurately and interpreting according to rules that no longer hold. The retina renders a heavy nucleus as a streak of light. The nose renders atomic oxygen recombining on cold steel as something burning. The auditory system renders a beat frequency between two oscillators as melody. In every case, the transduction is correct and the interpretation is terrestrial, and the gap between them is where the strangeness lives. 2 months after Apollo 10 heard its music, 2 men opened a hatch on the lunar surface, walked on the moon, and came back inside carrying something on their boots. When they removed their helmets, they discovered that the sense they had not thought about was the one with something to report. The lunar module Eagle was pressurized, the helmets were off, and there was a smell in the cabin that nobody had planned for. Buzz Aldrin described it as spent gunpowder, the odor in the air after a firearm has been discharged. Neil Armstrong, in his own account, reached for the same comparison and called it wet ashes in a fireplace. Later crews said the same thing without prompting. Harrison Schmitt, the only professional geologist to walk on the moon, and therefore the person on the entire program best equipped to characterize a rock by any available sense, reported the gunpowder odor and then went further. He developed what the flight surgeons logged as lunar dust hay fever, with congestion and sinus irritation that appeared shortly after ingress and faded over several hours. Gene Cernan noted it too. The consistency across missions is total. Every crew that brought dust inside smelled the same thing. There is an immediate problem with the comparison, and it is the same problem the airlock smell presented, only sharper. Gunpowder smells the way it does because of specific combustion products, sulfur compounds, nitrogen oxides, partially burned organics, the residue of a rapid oxidation reaction. None of those chemicals exist on the moon in any quantity. The lunar surface is anhydrous, has no free oxygen, no organic chemistry to speak of, and no history of combustion. Whatever the crews were smelling, it was not the products of burning, because nothing there has ever burned. So the question is, what a person is actually detecting when they inhale lunar dust in a pressurized cabin. And the answer requires understanding what the dust is, and more importantly, what it has never had a chance to do. Lunar regolith is the product of impact. With no atmosphere to stop them and no water or wind to erode anything afterward, meteoroids of every size have been striking the surface continuously for 4.5 billion years. Large ones excavate craters. Small ones, micrometeorites, grains of interplanetary dust arriving at tens of kilometers per second, do something more consequential over time. They pulverize. The surface is a layer of shattered rock several meters deep, ground progressively finer by an unending bombardment, with a substantial fraction of the material at the top existing as particles under 20 microns. Some of it is under a micron, small enough to behave like smoke. The grains have a specific character that follows from how they were made. Terrestrial dust has been through water and wind, and both round things off. A grain of sand on a beach is smooth because it has been tumbled. Lunar grains have never been tumbled by anything. They were fractured by impact and left exactly as the fracture created them. Angular with sharp edges, conchoidal fracture surfaces, and in many cases fine glassy spines. Micrometeorite impacts also melt small volumes of material, and the melt splashes and welds fragments together into structures called agglutinates, irregular clumps of glass and mineral shards with cavities and protrusions, unique to airless bodies. Under a microscope, lunar dust looks less like sand than like broken glass mixed with barbed wire, That geometry is why it stuck to everything. Apollo crews found the dust adhering to suit fabric, working into every seal, coating tools, and refusing all attempts at removal. The brushes did not work. The mechanical interlocking of angular grains with woven fabric is essentially irreversible, and the dust was further held by electrostatic charge. The surface is exposed to solar ultraviolet, which liberates photoelectrons and leaves the grains positively charged during lunar day. Charged, sharp, and dry, the dust behaved less like a contaminant than like an adhesive. Apollo 17's crew reported that the seals on their suits were abrading, that the dust had worn through layers, and that after 3 days of surface operations, the equipment was visibly degrading. Cernan remarked that dust was the most significant inhibition to lunar surface operations. An engineering assessment, not a complaint about tidiness. But the odor requires more than geometry. It requires chemistry, and specifically it requires understanding what the vacuum does to a freshly broken surface. When a mineral fractures, the break severs chemical bonds. On either side of the new surface, atoms are left with unpaired electrons, dangling bonds in the language of surface chemistry, and they are energetically unhappy. On Earth, this condition lasts nanoseconds. The moment a rock breaks, the exposed surface is struck by an enormous flux of atmospheric molecules, oxygen, nitrogen, and above all, water vapor, which is present everywhere and which adsorbs onto almost any mineral surface within moments. The dangling bonds are satisfied. The surface passivates. Every mineral grain you have ever encountered has been chemically saturated for as long as it has existed in air. On the Moon, that never happens. A grain fractured by a micrometeorite impact retains its dangling bonds indefinitely because there is nothing to feed them. The ambient pressure at the lunar surface is on the order of a trillionth of Earth's, a better vacuum than most laboratory equipment produces. There is no water vapor, no molecular oxygen, nothing to adsorb. The grain sits there chemically activated for however long it takes until something changes. There is a second process operating alongside this. The solar wind strikes the unshielded lunar surface directly, and it consists largely of protons, hydrogen nuclei, arriving at hundreds of kilometers per second. They implant themselves into the top layers of every exposed grain. Over geological time, this does two things. It saturates the regolith with hydrogen, and it chemically reduces iron oxides in the surface layer, producing nanophase metallic iron. Particles of pure iron, a few nanometers across, embedded in the rims of the grains. This is the process that darkens airless surfaces over time, called space weathering, and it means the dust is not merely inert silicate. It carries free metallic iron at the nanoscale, which is about as reactive a form of iron as exists. So consider what was carried into the lunar module. Several kilograms of extremely fine, sharp-edged, chemically starved mineral particles, saturated with implanted hydrogen, studded with nanophase iron with unsatisfied bonds on every fracture surface, in a state that no terrestrial material has ever occupied. Then the hatch closed and the cabin filled with oxygen at a third of an atmosphere, containing water vapor from 2 humans breathing. The dust reacted, all of it at once across an enormous aggregate surface area. Fine particles have surface areas per gram that dwarf anything coarse. The dangling bonds found partners, water adsorbed. The nanophase iron oxidized. Implanted hydrogen was released and could form compounds with whatever it found. Each of these reactions is exothermic, and each produces trace volatile species that a human nose is exposed to at close range in a very small sealed volume. The gunpowder comparison on this reading is doing precisely what the seared steak comparison did in the airlock. The nose detected the signature of rapid oxidation, the products of a reduced material meeting an oxidizer, and reported the only category it has for that signature, which is combustion. There was no fire. There was, chemically speaking, something closely resembling the aftermath of one, distributed across a few kilograms of powder that had been waiting 4 billion years for oxygen. There is a piece of supporting evidence in the sample archive that makes this uncomfortably clear. The returned lunar samples do not smell. They were sealed on the moon, opened on Earth, and by the time anyone put a nose near them, the reactive surfaces had long since found something to react with. During transfer, through seal leakage, or in the first moments of exposure. The odor was a property of freshly exposed dust in a freshly pressurized cabin. It could not survive the trip. The only humans who will ever smell it are the ones who are there when the hatch closes. The health question follows directly and is not settled. Schmidt's hay fever was transient, but the properties that produce the smell are the same properties that make the dust a respiratory hazard. Fine enough to reach the deep lung, sharp enough to damage tissue mechanically, chemically reactive enough to generate free radicals on contact with lung fluid. The comparison drawn most often is to silicosis, the fibrotic lung disease produced by inhaling fine crystalline silica, which has killed miners and stonecutters for centuries. Lunar dust may be worse because terrestrial silica is at least chemically passivated. Ground-based studies exposing cell cultures and animal models to lunar simulants, and in limited quantities to actual returned regolith, have found toxicity that correlates with the reactivity of the surfaces rather than merely with particle size. Apollo crews were exposed for hours or days. A permanent base would mean exposure over months, with dust tracked in every airlock cycle, accumulating in filters and fabric in the corners of every module. This is now recognized as one of the more serious unsolved problems in lunar surface architecture, and considerable effort is going into dust mitigation. Electrostatic removal systems, suit ports that keep the suit permanently outside, magnetic separation that exploits the nanophase iron. All of which began as a remark from two men taking off their helmets and noticing that the cabin smelled like a firing range. And the dust does something else that Apollo only glimpsed. Before sunrise, the surveyor landers photographed a faint glow above the lunar horizon. And the leading explanation involves the same electrostatic charge that made the dust cling, acting on a surface with no wind to move it. There is a region of sky above the South Atlantic where the instruments start reporting things the instruments in every other region do not. The pattern is entirely predictable, which is what makes it useful. As the station approaches a broad zone centered roughly over Brazil and extending east across the ocean towards southern Africa, radiation counters climb. Not gradually, the rise is steep, and within minutes the dosimeters aboard are reading many times their background value. Single event upsets in computer memory increase. Laptops freeze and require rebooting. Some instruments are commanded off before entry and back on after exit, because the alternative is corrupted data. Crews report an elevated rate of the light flashes described earlier, closing their eyes and seeing streaks at a frequency well above what the rest of the orbit produces. Certain operations are simply not scheduled during the passage. Extravehicular activity is planned around it. Then the station exits, and the counters fall, and everything returns to normal until the next pass. The station crosses this zone several times a day. It is not an anomaly in the sense of something unexplained. It is an anomaly in the technical sense, a departure from the expected value of a field, and the field in question is the magnetic one that surrounds the planet. The naive picture of the Earth's magnetic field is a bar magnet at the center, producing a clean dipole with the axis running roughly north to south. That picture is a first approximation, and it is wrong in specific ways that matter. The field is generated by convection in the liquid iron of the outer core, a self-sustaining dynamo in which moving conductive fluid generates a field which in turn organizes the fluid motion. The process is turbulent. The result is a field that is dipolar to a good approximation, but carries substantial non-dipolar structure, and that structure moves. Two features of the real field combine to produce the anomaly. First, the magnetic axis does not pass through the planet's center. It is offset by several hundred kilometers, which means the field is systematically stronger on one side and weaker on the other. Second, beneath the South Atlantic, there is a large region where the field at the core mantle boundary is reversed relative to the dominant polarity, a patch where the flux points inward instead of outward. This is called a reversed flux patch, and it subtracts from the total field strength at the surface above it. The consequence is a broad depression in field intensity over South America and the adjacent ocean. The field there is weaker than at comparable latitudes elsewhere by a substantial margin, roughly 35% below what the simple dipole model predicts. That weakness has a specific effect on the radiation environment, and the effect is geometric rather than direct. The Van Allen belts are regions where charged particles, protons and electrons captured from the solar wind and produced by cosmic ray interactions, are trapped by the magnetic field. A charged particle in a magnetic field cannot cross field lines freely. It spirals along them. As it moves toward a pole, the converging field lines slow its parallel motion until it reverses, the magnetic mirror effect, and it bounces back toward the other hemisphere. The result is a population of particles bouncing between the poles, drifting slowly in longitude and remaining trapped for periods that can extend to years. The inner belt, dominated by high-energy protons, normally has its lower boundary well above the station's altitude, around 1,000 kilometers or higher. Crews at 400 kilometers fly comfortably beneath it, but the belt's shape is not defined by altitude. It is defined by the magnetic field, and it follows the field's contours. Where the field is weak, the belt sags. Over the South Atlantic, the inner belt's lower boundary descends to roughly 200 kilometers, below the station's orbit. The station does not fly under the radiation belt there. It flies through it. That is the entire mechanism. There is nothing exotic in the sky over Brazil. The station's altitude has not changed. What has changed is that the magnetic structure holding the particles has dipped, and the vehicle's fixed orbit intersects a boundary that is moved down to meet it. The operational consequences are handled routinely, and the handling is instructive. Roughly half of the total radiation dose accumulated by an ISS crew member over a long-duration flight comes from these passes, despite them occupying a small fraction of the time. The Hubble Space Telescope cannot make observations during its crossings. Its instruments are shut down for a portion of every orbit, which costs a meaningful fraction of its available observing time. Satellite operators design around it, hardening electronics or accepting that certain systems will need to recover from upsets on schedule. Some spacecraft failures have been traced directly to it. The reason the effect on electronics is so specific comes down to what a proton at these energies does to a semiconductor. Modern memory stores a bit as a small quantity of charge in a small volume. A single energetic proton passing through that volume deposits enough charge along its track to flip the state. A single event upset. In a well-designed system, this is caught by error correction and corrected invisibly. In a laptop that was designed for an office, it is a crash. The station's crew laptops are ordinary commercial machines, which is a deliberate choice. They are cheap, replaceable, and can be rebooted. And their behavior over the anomaly is the price of that choice. The more interesting question is what the anomaly is doing over time, and the answer is that it is not static in any respect. Direct satellite measurement, principally from the Swarm constellation, has tracked the region continuously for years. The field within it is weakening. The region is growing in area. It is drifting westward at a rate consistent with the general westward drift of the field's non-dipolar features, which is itself a signature of fluid motion in the outer core relative to the mantle above it. And most notably, the anomaly appears to be splitting. Recent data show a second lobe of weakened field developing over the southwest of Africa, distinct from the primary minimum over South America. Two centers where there was one. Meanwhile, the dipole component of the global field has been declining measurably since systematic magnetic observation began in the 1830s, dropping by roughly 9% over that period. The temptation is to connect these facts to a reversal. The geological record establishes that the field reverses polarity, north and south exchange, at irregular intervals, on average a few times per million years, with the last full reversal occurring around 780,000 years ago. That interval is longer than the average, which invites the inference that one is overdue. The inference does not hold up well, and the reasons are worth stating precisely because this is a case where the honest scientific answer is more interesting than either of the confident ones. Reversals are not periodic. The intervals between them are distributed in a way consistent with a random process, and a random process has no memory. Being a long time since the last one provides no information about the next. The current field strength, despite the decline, remains within the range the paleomagnetic record shows for the past several million years. It was substantially higher 2,000 years ago than now, and the decline may simply be a return toward the long-term mean, rather than the beginning of anything. Numerical dynamo simulations do show reversed flux patches developing at the core mantle boundary before reversals, which is suggestive. But they also show such patches forming, drifting, and vanishing without any reversal following. The South Atlantic anomaly has probably existed in some form for a considerable time. Paleomagnetic evidence from archaeological materials in southern Africa suggests recurring field weakness in that region over the past millennium, and possibly much longer, hinting at a persistent structure at the core mantle boundary beneath it, perhaps related to a large, dense province in the lowermost mantle that disturbs the fluid flow above it. So the field is weakening and the anomaly is growing, and these are measured facts. Whether they are the early stages of a reversal or a fluctuation of the sort that has occurred repeatedly without consequence is not currently determinable, and claiming otherwise overstates what the data support. What is determinable is that a reversal, if one occurred, would not be an event. It would be a process taking somewhere between 1 and several thousand years, during which the field would not vanish but would become weak and multipolar, several poles instead of 2, wandering. The surface would receive more cosmic radiation and more solar particles. Auroras would appear at low latitudes. Satellites would suffer. The correlation between past reversals and biological extinction has been searched for repeatedly and has not been found, which is the strongest available evidence that life handles it. For the crews, none of this is abstract. They fly through the weak spot several times a day and watch their equipment respond to it. The anomaly is the only place where the planet's magnetic field is directly perceptible as an experience rather than a measurement, where its absence rather than its presence is what registers. And that raises a different question about the crews themselves. Everything discussed so far has been an external phenomenon reported by a reliable instrument, but the instrument is a human being confined in a small volume, for months, in an environment that provides almost nothing the nervous system evolved to expect. What happens to the observer is its own subject, and the agencies study it with the same seriousness they apply to hardware. The clinical term is the third quarter phenomenon, and it was named by researchers studying Antarctic winter overcruise long before anyone applied it to spaceflight. The pattern is consistent enough to be scheduled around. In any confined, isolated, extended deployment, morale follows a curve. The first quarter is occupied by novelty and by the sheer volume of things that must be learned. The second quarter is productive. The third quarter, regardless of the mission's absolute length, whether it runs 6 months or 14, is where problems concentrate. The novelty is gone. The end is not yet close enough to count down toward. Interpersonal friction that was tolerable becomes less so. Sleep degrades, motivation drops, and perceptual oddities begin to appear in the debriefs at a rate that is not observed in the first or last quarters. That the curve scales to mission duration rather than to elapsed time is the detail that makes it a psychological phenomenon rather than a physiological one. Bodies do not know what fraction of a deployment has passed. Minds do. Space agencies treat this with the same procedural seriousness they apply to a thermal control loop, and for the same reason, it is a predictable failure mode with identified mitigations. The station's schedule includes protected time, family conferences, and a deliberate distribution of tasks designed to prevent the third quarter from being the monotonous one. The crew's psychological support staff monitor voice loops for markers that precede a decline. None of this is precautionary theater. Confined environment research from submarines, polar stations, and long-duration analogs converges on the same finding, which is that the mind in an unvarying environment does not simply endure it. It compensates. The compensation is the interesting part, and it follows from how perception actually works. The intuitive model of perception is that the senses deliver data and the brain reads it. This model is wrong in a way that matters here. The brain does not passively receive, it predicts. It maintains a running model of the environment and uses incoming sensory data primarily to correct that model where it errs. What reaches conscious experience is not the raw signal but the model, the prediction, updated. This architecture is enormously efficient because most of the world is stable most of the time, and predicting it costs far less than measuring it. It is also the reason perception degrades in specific, characteristic ways when the incoming data thins out. If the sensory input is impoverished, if the environment provides very little to correct the model with, the model runs with less constraint. It continues generating predictions because that is what it does, but the error signal that normally disciplines those predictions is weak. The result is that the internally generated content, which is always present and normally suppressed beneath the flood of real input, becomes proportionally more prominent. It surfaces. This is not speculation about spaceflight. It is a robust laboratory result with a long history. Sensory deprivation experiments, beginning with work at McGill in the 1950s and repeated many times since under better conditions, reliably produce perceptual anomalies in ordinary volunteers within hours. Not in unstable people and not as a sign of pathology. In students paid by the day, lying in a dark, quiet room. The reported effects run from simple geometric forms to complex structured imagery, from a sense of presence to distortions of body schema. The Gansfeld procedure, which floods the visual field with unstructured uniform light rather than removing it, produces similar results faster. Given a visual field with no edges, no contrast, no information at all, the visual system does not report nothing. Within minutes, it reports something, because a system built to find structure will find it in noise if noise is all there is. The mechanism generalizes. Charles Bonnet syndrome, in which people losing their vision experience detailed and often elaborate visual hallucinations while remaining fully aware that they are not real, is the same principle operating in a clinical population. The visual cortex has not been damaged. It has been deprived of input, and it fills the vacancy from its own resources. Musical ear syndrome does the same thing in the auditory system of people going deaf. In each case, the hallucination is not a malfunction of the perceptual system. It is the perceptual system continuing to function correctly in the absence of the data that normally constrains it. An orbiting spacecraft is not a deprivation chamber. It is loud, mechanically busy, visually cluttered, and demanding. But it is profoundly monotonous along the specific dimensions the nervous system evolved to track, and monotony is the operative variable rather than silence. Consider what is absent. There is no weather. Temperature and humidity are held within a narrow band by design, permanently. There is no day in the sense the circadian system understands. The 16 sunrises provide a light cycle the hypothalamus cannot use, and the artificial schedule imposed to replace it is a fiction the body accepts imperfectly. There is no walking, which removes a rhythmic proprioceptive input the brain has received continuously for the entire evolutionary history of bipedal locomotion. There is no down, so the vestibular system's otolith organs, evolved specifically to detect the direction of gravity and useless without it, deliver a null result to a brain that has no prior for a null result and must build one. That last item produces some of the more striking reported effects, and they are physiological rather than psychological, which is why they are useful for calibrating the rest. The vestibular system reports both linear acceleration and orientation. In orbit, the otoliths continue reporting acceleration during head movement, but never report a gravity vector. The brain, which has spent a lifetime integrating vestibular data with visual data, under the assumption that one particular direction is down, receives a conflict it cannot resolve. Early in a flight, this produces space adaptation syndrome, nausea, disorientation, difficulty tracking. Within days, the brain reweights, essentially discarding the otolith contribution to orientation and relying on vision instead. It builds a new model. The consequence is that up becomes whatever the eyes say it is. Crews report that orientation within a module can flip on attention, that a wall becomes a floor because they decided to treat it as one. Some report entering a familiar module in an unfamiliar attitude and failing entirely to recognize it, experiencing a room they have occupied for months as a place they have never been until they rotate and the model snaps back. The room did not change. The reference frame did. This is a clean demonstration of the general principle, and it should inform how the other reports are read. Perception is a construction. The construction is normally so well constrained by input that it is indistinguishable from a direct reading of reality, and in ordinary environments, the distinction is philosophical rather than practical. Change the environment enough, and the distinction becomes operational. It becomes something that happens to you. Against that background, the psychological reports from long-duration flight are less mysterious than their reputation suggests, and better documented than most people assume. Crews report time distortion. The sense that duration has stopped tracking against clocks, that a week and a month feel similar, which follows directly from the removal of the environmental markers that normally punctuate memory. They report a sense of presence, the impression that someone is nearby when nobody is. This is common in isolation generally, well documented among solo sailors, high-altitude climbers, and polar personnel, and it is understood as the social cognitive equivalent of Charles Bonnet, a system built to model other minds continuing to model in their absence. They report most consistently something at the other end of the spectrum entirely. The literature calls it the overview effect, and the term has accumulated enough popular use to obscure that it is a real and studied phenomenon with a plausible mechanism. Crews looking at the planet report a shift in the salience of categories that had previously seemed fundamental: borders, nations, the boundaries of the self. Some report it as a cognitive change that persists after return. The mechanism is not mystical, and it is worth stating plainly. Human spatial and social cognition operates on a scale calibrated by experience. A person who has never seen the planet as an object has no perceptual representation of it, only an abstraction, a fact known but not seen. Presented with the object itself, the cognitive system does what it does with any novel object. It integrates it into the model. And the integration has consequences because a great many concepts that felt like features of reality turn out. Once the planet is visible as a single finite thing to have been features of a particular scale of observation. The reaction is not sentiment, it is the correction of an error that could not be detected from inside. Which brings this back to where it began, and to what the whole archive of strange observations actually demonstrates. Every phenomenon in this account resolved into the same shape. A sensory system evolved over hundreds of millions of years in one atmosphere at one gravity, under one star, calibrated exquisitely to an environment it never left, and then moved. The retina, presented with an iron nucleus from a dead star, reports light, because light is what the retina reports. The nose, presented with atomic oxygen finding a partner after 300 kilometers of waiting, reports burning because burning is the only category it has for oxidation. The ear, presented with two oscillators drifting against each other in a silence more complete than any on Earth, reports music. The visual system, presented with an object against a background containing no information, computes a size because a percept requires one, and the system cannot decline to produce it. In every case, the transduction was correct. The signal arrived, was faithfully converted, and was accurately reported. What failed was never the instrument. It was the interpretive layer, the set of assumptions so deeply built in that no observer can see around them, because they are not something the observer has. They are something the observer is. 700 people have been in a position to notice this. Their reports are strange not because space is strange, but because the reports are the first data we have ever obtained about what human perception does when its assumptions are removed. Every one of those observations is, read correctly, less a description of the environment than a measurement of the observer. And the observers are still up there several times a day, closing their eyes over the South Atlantic and watching the light arrive.